Welcome to week 7 of computational thinking. This week we'll be talking about the tree data structure. So in terms of the roadmap, you can see that we start with the simplest data type called the linear data structure. Now we are in the middle. We will be introducing hierarchical data structure. This is our first attempt, try to capture the relationship. Then in the next session, week 9, we're going to talk about probably the more complicated type of relationship. It's called the graph data structure that allow you to capture arbitrary type of network. So the objective for today is to first introduce binary tree and binary search tree. How do we use it in general? And then we can demonstrate like the classical use cases of how those kind of these two different data type is of critical importance to various different kind of application. Here you're going to see 3 different data type with increasing specialization. Tree is the most general type of hierarchical data type. Then we begin to specialize. We have binary tree, and finally we have the most specialized version called the binary search tree. Right? You'll see what's their definition, how they can be used. In terms of references, we are now at the chapter 2 of the data structure handout. You can find it on eLearn, and also we have our tree lab Python library for you if you want to play around with the data type. If you prefer online version, you can access exactly the same database code base on Colab. We have created a notebook for you. Inside it, besides the like standard test code, you can also find all the examples, all the different use cases that we have talked about in class. So you're welcome to try it out. But of course, you can replicate everything that we have shown online by using the tree lab that's provided to you. Right, so a little bit of recap. When we introduced the linear data structure last week, the major thing that's really making it linear is internally, all the data that we are storing, they follow a linear relationship. So it's going to be one after the other. So the reason why it's special, is different from the list, is that if you look at it for the 3 different data type we have introduced, stack and queue, they pretty much just open up a single place for inserting data and a single place for removing and retrieving data. And depending on the rule that you specify, you will generate different kind of data structure. For example, for stack, the rule specified that if you need to insert the data or if you want to remove the data, both will be occurring at the top of the stack. Okay, and because you retrieve and you insert data at the same place, you have this special property of last in, first out. And for the queue data, we modify the rule a little bit, right? So when you insert the data, it's going to be at the tail of the queue, just like a real queue, right? And when you remove the data or retrieve the information, it's going to be at the head of the queue, right? So this basically gives you a special property of first in, first out. And finally, we also have the priority queue, which basically says that instead of using arrival time to determine the sequence of data retrieval, now we actually have a special property called priority. When you are about to retrieve the data, you're going to return the data that's with the highest priority, which can be a user-defined property if this is a complex object that you try to store inside the queue. Right, but regardless of how, like, what the rule really is, this whole collection of data type, stack, queue, and priority queue, they still pretty much just follow this guiding principle that all the data have a clear before and after relationship. But sometimes the relationship is not so linear, right? So if you do not have just before and after, you have more than that, then the linear data structure cannot capture it. So we start with the simplest relational data that doesn't contain only the linear relationship. We call it the tree. It's called a tree because literally, I mean, if you take an inverse view of this tree on the right hand side, you will see that for each and every, for example, each and every node over here, it leads to like 2 additional data points, which are related to the one that we begin with. And this kind of relationship is hierarchical in nature, is one layer after the other, right? Also, after that, right, if our relationship is even more complicated than that, you don't have a clear level by level hierarchy. Instead, anybody inside the network can connect to anybody else. Your data is not non-hierarchical. Then we need the final data type, which is going to be introduced next week, is called the graph data type. So a lot of example actually exists to demonstrate what a tree is. And this is, I think, the easiest example that you see on a daily basis. You open up your file explorer, your Finder. You will see that, for example, starting from the highest level, let's say you start with slides, you click on that, you see a whole bunch of other folders that belong to this parent folder slides over here, right? And then you can pick another folder that's underneath slides, for example, week 7. Then you have all these files that belong to week 7. So if you look at each and every file, right, or each and every subfolders, you actually have a parent folder. This is like a relationship, a single relationship. Every file, every subfolder should have a single parent folder. But on the other hand, if you look at a particular folder, potentially you can have a lot of subfolders or subfiles that's being stored underneath it, right? So this is the classical property of the tree data structure. Single file can only be associated with a single parent directory. But under a directory, you potentially can have a lot of files that's being stored inside. Similar property can also be observed from the family tree, right? And this is one of the most famous tree in the United States. For you pick any particular person, for example, Patrick Kennedy, right? So this person within the family, definitely you will have like one father, one mother, right? That will be your parents inside the tree, and then your parent will have their parents, so on and so forth. So you can keep going until you reach the head of the household. Or you can use it to model the organization chart for any company as well. You can, for example, start with the CEO, right? Which usually this is what we call the root node, right? And progressively you can go down the layers, and then eventually, if you reach the lowest layer and you do not have any further nodes, this is what we call the leaf nodes. All right. So again, if you observe the structure, this is the very special type of relationship. You pick any nodes, for example, over here, a particular manager, you look up, right, from this particular leaf node, you should have only a single parent. But if you look at a parent, a particular node over here, potentially you can have multiple children nodes, right? So this is the special property of the tree. You have a single parent, but you will have potentially multiple child nodes, right? So just to get the terminology aligned, because I think different textbook or different articles may define these two properties, level and height, slightly differently. So throughout this particular lesson, when we refer to the level will be starting from 1, right? So the root level, which is the highest level, will be level 1. And then the children of the root level will be 1 level more, right? So effectively, you start from 1, 2, 3, all the way until the deepest level. And the height of the tree is defined based on the maximum level, right? Usually we'll use H to represent that. And the special case will be the tree that doesn't have any nodes in it. In that case, this particular empty tree, we define the height to be 0. All right, so this is the definition. Right, so based on this definition, actually, we can then define different type of relationship within the tree. The most straightforward one, this is the one that we talked about earlier, is the direct relationship, right? So you have a parent, then you can have a child node. And vice versa. For any node, you can actually try to identify your parent node, right? The only node in the tree that doesn't have a parent node will be the root node, right? Because this is the beginning of all the hierarchical relationship. All right, if two nodes, they are being separated by multiple nodes in the hierarchy, this is what we call the ancestor and descendant, right? For example, like if you just track in the previous organizational chart, all the manager nodes, right? So if you backtrack this manager node, you can actually trace back all the way to the CEO node, right? So in other words, from the manager's perspective, CEO will be considered as the ancestor node. But if you go from CEO's perspective, then all the manager will be considered as the descendant of the CEO. Finally, sibling, right, is the case where you do not have direct or indirect linkage, but instead you are sharing the same parent node. Right? One example is that managers, they potentially, if they are belonging to the same functions, then they will be considered as sibling in the organization. Right. So we talk about like how recursion can be useful in representing concept, in representing the algorithm design. In the context of the tree, this is the best example. Right. So if you look at the definition of the tree, it's actually completely recursive. Right. So when we define the tree, you always start with the root node. Right. So in this case, CEO will be our root node. And after you define the root node, you can potentially have either if you are the only node in the tree, then you have no subtree at all. This is zero subtree case. But in this case, right, you can look at this CEO node, and you can identify that we actually have 3 different subtrees. And for each and every subtrees, they respectively can be treated in the same way as the tree that we begin with. Right, so every subtrees will have their respective root node as well, right? And this just repeat until eventually you have a single node inside the tree. That will be the leaf node, right? So we have been talking about a general tree. General tree basically means that for each and every node, there's no limitation as to how many child nodes you can have. But a special case where you only have 2 children for each and every node is called the binary tree. Again, this binary refers to the fact that you only have at most 2 child nodes. You don't have to have 2 child nodes for every node, but if you have indeed child nodes, then 2 is the maximum number. Right? If that is satisfied for each and every node, we call this kind of tree a binary tree. So terminology are pretty much the same. We still call the highest level of the node as the root node. The lowest level are still called the leaf node. But additionally, we still call like all the nodes in between internal nodes. So with the binary tree, then we can define the special type of the binary tree depending on their shape. The first type of binary tree will focus on whether or not every node have complete fill up, right? So if you look at it, if each and every node have exactly 2 children or no child at all, if that is the case, we call this kind of tree full binary tree. And on the right hand side, you can see this is one example. If you check each and every node, either you have 2 children or you have no nodes at all, right? For example, all this node over here, they are the leaf node, right? But if you outside of the leaf node, if you look at their parents, they will have exactly 2 children, right? So this is the case where the tree is full. The binary tree can also be complete. Right, this is not to be confused with the full binary tree. Right, full binary tree, you can see that the shape can be pretty arbitrary. Right, only requirement is that if you have a child nodes, then it has to be 2. Otherwise, you have to be the leaf node. But the complete binary tree basically means that each and every level need to be completely filled. And the only exception is the lowest level. This is the level H, right, at the height of the tree, which is the lowest level. you can have vacancies, but vacancies need to be on the right hand side, right? So all the nodes, if you have it, need to be squeezed to be as left as possible. If that is the case, we call this kind of binary tree the complete binary tree. Finally, this is a special case where for each and every level, all the space are fully utilized, right? So this is what we call the perfect binary tree. All right, so a natural question that can be asked over here is that if we know the height to be h, then how many nodes will this particular tree be able to hold, right? So you can probably pause here for a while if you want to give it a try before we progress to the answer. All right, so I hope that you can actually come up with this by yourself, but in case you're not sure, this is the process of the reversion, right? Let's say we use this particular example. This is level 1, this is level 2, this is level 3, right? So if you look at it, the numbers of nodes that you have at level 1 is 2 to the power of 0, right? A single node. For level 2, because this is a perfect binary tree, one node becomes 2 nodes. So the numbers of nodes that you have from previous case, which is 1, will be multiplied by the fixed factor of 2, right? So now you have 2 to the power of 1. For the lowest level, right, you have 2 nodes over here. So for each and every node, you have exactly 2 children, right? So 2 to the power of 1 will be multiplied by 2 again. So the next level, at level 3, you'll have 2 to the power of 2 nodes. If you generalize it, like if your height is actually h, right? The lowest level will be 2 to the power of h minus 1. This is the numbers of times you're going to multiply by 2. So if you sum it up, right, the total numbers of nodes will be 2 to the power of 0 plus 2 to the power of 1 plus 2 to the power of 2 until, right, the lowest level, you have 2 to the power of h minus 1. This is the total numbers of nodes that you can hold if your binary tree is perfect. And this is what we've seen before. This is called the sum of geometric series. So again, over here, we can try to recognize the terms in the formula. The first term is actually 1. R, which is the fixed factor, is actually 2. The numbers of terms that we have over here is actually h, right? From 0 to h minus 1, right? Okay, so because of that, we can utilize the formula. R minus 1, which is 2, minus 1, A1, which is 1, and then you have R to the power of numbers of terms, h minus 1, right? And this is just 1. This one is 1, right? So the numbers of nodes you can hold as a result will be 2 to the power of h minus 1, right? So if you want to test this formula, I think this example on the right hand side is easy, right? So we have h equals 3, and based on this calculation, we should have 1, 2, and 4, right? So in total, we have the numbers of nodes is actually 7. If you use the formula, it should be 2 to the power of h, 2 to the power of 3 minus 1, which also give you 7, right? So at least for this simple example, this formula is correct, right? If you want to double check, you can try the case of like h equals 4, just one level more, and you'll get the same result. Okay, so this is another application of the sum of geometric series formula. Right, so that tells you the capacity of your perfect binary tree, the most numbers of nodes that you can hold. Right, so why do we highlight only the binary tree? Because like, if you have a general tree, you can actually store arbitrary numbers of nodes, right? Okay, the reason why binary tree is particularly important is for the first two example, right? So we previously towards the end of the last session, we said that in order to efficiently implement priority queue, you must be able to very quickly retrieve the node that currently have the highest priority. And to do that, I mean, in practice, the most effective way is to maintain something that's close to binary search tree, right? So the special type of tree that can actually satisfy this priority queue requirement is called the heap. Right, later you will see the binary search tree, how it works and why it is efficient. And following that, right, so I mean the binary tree can also be used to do the data compression, right? So all the well-known like the data compression method, whether or not it's a file, is audio, is image, or even is the video, right? You can all trace its implementation back to certain kind of binary tree, right? And we call it the Hoffman coding tree. This is how you can actually compress the data. Finally, right? So I think syntax tree is very widely used in all kinds of expression or all kinds of programming language. So whenever you write a code fragment, you see the way that computer actually process your program is to first, through some unified approach, turn your program into a tree, just like the right-hand side. It's not really a binary tree per se, but is a general tree structure. And from the tree, you can see that every node will have like different properties. Some of the node represent the keyword of the language. Some of the node here represent the variable, and some of the node represent the value. They are being labeled as different color. And then after that, after you have this conversion process done, then we have a tree interpretation algorithm that will work over the tree starting from the root node. And then based on the results, we can then execute the proper steps or execution code that's associated with each and every node, right? So this is how computer, regardless of the environment, they can very consistently execute the code that you provide. So now we are down to the implementation, right? So this is another reason why the binary tree is strongly preferred as the tree data structure, right? Because to represent a binary tree, you can actually represent them as the node. And for each and every node, the data you need to store inside is fixed, right? So this is unlike the case of the general tree, where you have unknown numbers of children, right? In this case, for binary tree, is always 2, right? So a node can have at most 2 child nodes. So it's either the left-hand side or the right-hand side. So inside the internal data storage, this is what we can do, right? For a particular node, right? This is the node object over here. We store inside, this is the actual value you plan to store. And then besides the value, you can have the left reference and the right reference. That will be pointed to like the respective node, right? And then you can construct your tree gradually this way. Right. Of course, if your child nodes is actually reaching the end, for example, here, let's say this is the leaf node, right? Then what it does is that the left-hand side and the right-hand side simply point to none, right? That indicates that you have reached the termination point. You do not have further node to be stored anymore. Okay, so because of that, the storage of the binary tree can be very efficient. Right? So you can construct a tree very easily, gradually by inserting a new node. And whenever a new node is created, all you need to do is to identify which particular pre-existing node will be the parent node to this newly created node. Right. So if we turn that into the implementation, this will be the kind of interface we are expecting. At the node level, right? This is the single node level. We are not at a tree yet. Tree will be built based on the node, right? But at the individual node level, here, everything above, this is the internal variable, right? So in terms of variables, we need to store the left-hand side and the right-hand side reference. And then we store the actual value for this particular node. In terms of functionality, right? So we can create the node. This is the creation node. Initially, there's no relationship. It only counts with the value. What should be the value that need to be set within this node, right? After you have that, then we can set the left-hand side. We can set the right-hand side. We can delete the left-hand side. We can delete the right-hand side, right? And with the node defined, now we have the binary tree object. All you need to do, you see, is you set a root node. After that, you see all the relationship will be automatically decided based on the internal structure of the node, right, that we see on the previous page. But the binary tree class does provide this two additional functionality, which give you the numbers of nodes and also the height of your tree. Right. Finally, we are at the traversal of the binary tree. One of the, I think, the major challenge in using the binary tree is that we actually have a nonlinear data structure. So there's no clear order as to how you can access the data. So we need a particular rule that can turn the nonlinear data structure into like a sequence that we can use. You want a sequence because later, I mean, if you want to access any information inside the binary tree, you would like to do it in a systematic manner. You make sure that you do not miss any information stored inside the tree, but also you do not want to repeat the information inside a particular node, right? So it should be a walkthrough algorithm that guarantees that each and every node will be visited eventually. So there are three different types of traversal depending on when you actually read the value of the node. We call it preorder, in-order, and post-order. This is the place where really recursion will help a lot, right? It will become clear shortly. So this preorder, in-order, and post-order refer to when should you actually read the value. If we read the value before we actually do the recursive call to the left and right, then this is called preorder. This pre represent the fact that we actually do the visitation before the other two recursive call, right? And this is one example, right? We enter the traversal always at the root node, right? And because we actually do the visitation before we do any recursion, and recursion actually starts from left and then followed by right. So in terms of visiting sequence, this is 1, right? And then after we visit the node, we branch to left, right? And once we enter the left, again, we visit the value, visit the node and read the value immediately. So this is the second sequence. Then we go to the left-hand side, right? Again, read the value, right? So this is the time when we are about to return, right? So at the node M1, we try left, nothing at the left, so we return, and we go to right. Again, nothing to the right, so we return, right? So then at this point, this recursion is done, right? So we can return back to the previous node. Now we are at VP1, right? So we have finished the left branch, so we are going to go to the right-hand side, right? So again, the moment we enter M3, we are going to visit the value. Then again, we do the same as M1. We try to visit left, nothing left. We try to visit right, nothing right. So M3 is marked as visited, fully explore. So after you finish M3, then you return. Now you can see that both left and right branch of VP1 has been done. So we will mark VP1 as done, right? So now we return to CEO, right? The whole left branch of CEO has been visited. Now we are ready to traverse the right-hand side. So right-hand side is VP2. Again, the moment we enter it, we do the visitation. This is the number 5. Then we try left-hand side, right? We go left-hand side. At M2, again, we try left, we try right. Then we mark M2 as visited. Then we return to VP2. It will try right-hand side, but immediately this is empty, so it returned. So VP2 is marked as finished. Finally, we mark CEO as finished as well, right? So the final sequence is 1, 2, 3, 4, 5, 6. This is what we call the preorder traversal. The in-order traversal is actually very similar. And you can see that this is the reason why it's called in order, right? Because the visitation and the reading of the value actually occur in between these two recursive calls. So we start with the root node as usual. We enter it. You see that we do not read the value yet. We are going to go all the way to the left until we finish left. Then this is the time that we can actually visit the node. Okay, so starting from CEO, we go left, right? VP1, again, we try to go left. At M1, We try to go left, nothing. Return, right? At the moment that we return, then we can visit the value. Then we will try the right hand side as instructed over here, right? Nothing. So we return. Upon return to VP1, right? So it means that for VP1, the left branch has been done. So we are going to read the value, which is 2. This is the second order that we have visited. Then we're going to visit the right, right? Go to right, which is M3. Again, we do the same, left, return, read, right? And then right, right? And at this point, M3 is marked as done. We return, MP1 is marked as done. Now we return back to CEO. This is the point that we finally will be reading the value of CEO, right? So now we are done with the first two command. We are going to do the recursion on the right hand side. We go to right hand side, you have VP2. Again, you go to left hand side, which is the M2. You try left, return, read the value, and then try the right hand side, and then you mark M2 as done, right? And then you return back to VP2. This time you can read the value, then you try right hand side, mark VP2 as done, return, mark CEO as done, right? So this is the sequence 1, 2, 3, 4, 5, and 6. Finally, we have post order. Yeah, also very similar. But now we need to finish both the left hand side and right hand side of recursion. Then after that, we can read the value. So again, we start from root node, go left, then we go left, nothing, go right, nothing. We will read, right? At this point, after we finish reading, this is considered as done. Then we return back to VP1. We go right hand side, left, right, and then we read the value. We mark M3 as done, right? So we then return. Now we can, because left and right are both done, M1 and M3 are done, so we can read the value. We can mark VP1 as done, and we return to CEO. Now we go right branch, right? And then we go left, right? And right, and then we read the value. We mark M2 as done, return back to MP2, VP2. We try the right, and we read the value, which is 5. We mark VP2 as done. Finally, right, you see that for the post order traversal, because we need to finish the left branch and the right branch recursion. So the visitation to the root node always will happen the last, right? So for the post order traversal, you can be sure that you should always, if you do it correctly, you should always visit your new root node the last. This is in contrast to the preorder traversal, right? Preorder traversal, you always visit your root node the first. Okay, so this is the 3 major traversal types, very important. This is how you can systematically visit each and every data that's been stored inside the node. This is how you can turn a nonlinear data structure into a linear sequence, after which you can then maybe search for information, or you can do some processing to make sure that each and every node will receive exactly one processing. Right, so I think you will need some practices. This is one example, 3 different examples that's generated. Right, so you can actually just give it a try. A very small one, slightly larger than the previous examples, but give it a try. Pre-order, in-order, post-order are really given to you. Use the principle we just mentioned. Try to generate a sequence. If you want animation, you want to like practice more, you can click on this website over here. It actually can allow you to automatically generate the binary tree, and you can use that to practice different kind of traversal, and it actually provide animation to tell you whether or not your answer is correct as well. Right, and then we have the class exercises 1. Please use this particular diagram, this example over here, to generate pre-order, in-order, and the post-order. Finally, we have the larger tree. Please also use that to practice the pre-order traversal, in-order traversal, and also the post-order traversal. Right, so we'll pause here. Do make sure that you go through those exercises. we will resume in the next video after you finish your exercises.